Now let us see how matrices are being added or subtraction, addition or subtraction, how we are performing on the matrices. For an example, I'll take two matrices, 2, 3, 4, 5. This is one matrix. I'm trying to add this matrix with another matrix called 1, -1, 2, 0. How addition or subtraction is being performed on the matrices? For example, addition or subtraction is performed on the matrices from element to element. Whether if you have to add, every element in one matrix has to be added to the corresponding element in the other matrix. Okay, suppose say this is equal to A and this is say suppose B. So A plus B, when you have to add, every element in A shall be added to the corresponding element in B. That means element at position 1 1 in A shall be added to element at position 1 1 in B. So the resultant matrix will have at position 1 1 position 1 1 element at position 1 1 of A plus element at position 1 1 of B. So here the first element will be position 1 1 here is 2, position 1 1 here is 1. So the first element will be 2 plus 1. Next, position 1 2 is 3, position 1 2 is minus 1 here. So the next element will be 3 plus minus 1. Next here 4 plus 2. Since the corresponding element to 4 in B is 2 and 5 at 2 2 position, here at 2 2 position is 0. So the corresponding element will be 5 plus 0. So the resultant is 3, 2, 6, 5. Okay, similarly subtraction also. Similarly, if you have to subtract, the same thing again I'll write 2, 3, 4, 5. I'll take another matrix 1, 2, 1, 3. How to perform subtraction? This is equal to again element to element. First element will be 2 minus 1 at 1 1 position. Second will be 3 minus 2 element by element. Third will be 4 minus 1 at 1 2 1 position. 2 2 position 5 minus 3. So the resultant is 1 1 3 2. So while performing addition or subtraction, what we have done is we have done the corresponding operation from element to element, which means here how many number of elements are available in whatever fashion. The same number of elements shall be available in the same fashion, which means the size of this shall be equal to the size of that. So if A here size of this size of A shall be equal to size of B, then only we can subtract or add two matrices. So if A and B are to be added or subtracted, size of A shall be equal to size of B. This is the condition for addition or subtraction. Let us see now about how matrices are multiplied. Matrix multiplication is of two types. Matrix can be multiplied with scalar and matrix can also be multiplied with another matrix. Okay, first let us see how a scalar multiplication is being done. Okay, suppose I have a number, say suppose 2, and I have a matrix, say suppose 2 3 5 4. Okay, this is the scalar. Say suppose this matrix I have denoted it as A. Now how you will multiply 2 with A, 2 with the matrix A is, you have to multiply the scalar with each and every element of the matrix. 2A will become 2 into each and every element. You have to do the multiplication 2 by 2, 2 into 3, here 2 into 5, here 2 into 4. So each and every element of the matrix gets multiplied by the corresponding scalar. For example, if it is minus A, it becomes minus 1 into 2, minus 1 into 3, minus 1 into 5, minus 1 into 4. For example, if it is 0A, which means 0. 0 into 2, 0 into 3, 0 into 5, 0 into 4, all zeros, it results in a null matrix. So here the answer is 4, 6, 10, 8. This is scalar multiplication. We shall see now how matrix are being multiplied, matrix multiplication, matrix to matrix. Say suppose I have two matrix. I'll write some trivial example 2, 3, 4 again with 1, 2, 3, 4. Okay, say this matrix is named A and this matrix is named B. Assume by multiplying A and B I got a resultant, say suppose C. The resultant matrix I am naming it as C, suppose. Okay, at any position of C, at any position ij, say suppose the element at any position ij, if that position I have named it as, say suppose small c ij, the element at any position ij in this C matrix is equal to, this will be obtained by multiplying ith row of A into jth column of B. Here in C, an element corresponds to ij position is the result of multiplication of or product of ith row of A into jth column of B. Here A is called pre-multiplier and B is called post-multiplier. A is called pre-multiplier and B is called post-multiplier. Okay, so in other words, if I say if two matrices are to be multiplied, how the elements in the resultant matrix we can derive is by multiplication of, suppose say ij position, element at position ij you need, that is the resultant of ith row of the pre-multiplier into jth column of the post-multiplier. Here in this case A is the pre-multiplier and B is the post-multiplier. We shall see in this case what is the first element. Say suppose element at position 1, 1. Element at position 1, 1. This is equal to first row of A in the above example, this example. First row of A into first column of B. Okay. Now this multiplication, since first row contains some number of elements and first column here also contains some number of elements, this multiplication how would you do is, this multiplication is carried out in analogous to, according to dot product of vectors. I'll show you how it will be carried out. This multiplication of first row of A into first column of B. What is the first row of A here? The first row is 2, 3. And the first column is here is 1, 3. Okay. How it will be carried out is element by element. 2 into 1 plus 3 into 3. This gives us 2 plus 9, 11. So the first element at position 1, 1 is 11. How the element has been arrived? The first row into the first column. I will write it more clear here. So I will write the matrix again. 2, 3, 5, 4 into 1, 2, 3, 4. So this is equal to, first position is 2 into 1. How I have arrived, I have explained here. At position 1, 1 will be first row of A into first column of B. So this is 2 into 1 plus 3 into 3. Now the position, this is 1, 1 position. The next element position is 1, 2. Okay. Now how 1, 2 is being performed? 1, 2. Here first row of A second column of B. What is first row of A? This one. What is second column of B? This one. Now multiply these two. Okay, so that will be 2 into 2 plus 3 into 4. Okay, the next element's position is 2 1. How it has to be multiplied? Second row of A into first column of B. So second row is 5 4. I'll use a different marker here for 2 1. So suppose I'll write it with crayon. So second row of A and first column. So second row of A into first column, second row 5 4 into 1 3, 5 into 1 plus 4 into 3. Rather I would write it with green ink only so that we can identify it better. So 5 into green ink. This is 5 into 1 plus 4 into 3. I'll represent it with the red so that it can easily be identified. So the next one is 2 2. Element at position 2 2. How it shall be arrived? Second row of A and second column of B. If you write properly, 5 4 into 2 4 means 5 into 2 plus 4 into 4. So this is the resultant matrix. Some we can do. This is 11, 2 plus 9. This is 4 plus 12, 16. This is 5 plus 12, 17. This is 10 plus 16, 26. So this is the resultant matrix. So how we are doing at any position ij, element at any position ij in the resultant matrix is the resultant of multiplication of ith row of the pre-multiplier into jth column of the post multiplier. For us to perform, I'll just erase it here. For us to perform this operation, okay, since we have to multiply the ith row of A and jth column of B, the number of elements in ith row of A. So the number of elements in ith row of A shall be equal to number of elements in jth column of B, without which the multiplication cannot be performed at all. Number of elements in jth column of B. What is actually number of elements in any row? It is nothing but, in this row what are the number of elements? It is nothing but equal to number of columns. So this is number of columns in A shall be equal to, this is number of elements in any column. In any column, what is the number of elements? It is nothing but equal to number of rows in B. So effectively, if you have to perform multiplication of A with B, A is being the pre-multiplier, B is being the post-multiplier, the number of columns in A shall be equal to the number of rows in B. Okay, the number of columns in A shall be equal to number of rows in B. Here what is A and B? A is the pre-multiplier. And what is B? B is the post-multiplier matrix. Similarly, if we have to perform, say suppose B by A, What shall be the condition? Number of columns in B shall be equal to number of rows in A. This shall be the condition. So if I have to perform any two arbitrary matrix, if A is of the size, say suppose m by n, in order to perform multiplication with B, post multiplication with B, B shall have same number of rows that are equal to the number of columns in A. So B shall be of the order n by any other arbitrary number. You can name it as P, say suppose. So the number of columns here shall be equal to the number of rows here. Now the resultant, what would be the resultant matrix size? These two shall be equal. The resultant matrix size will be m by P. Okay. One small example we'll see. One more example. Say suppose one matrix is like 1 0 0 0 2 3 1 5 1. This is one matrix. I am taking a matrix here. Since this is 3 by 3 matrix, as you can see 3 rows and 3 columns are there. So this is 3 by 3 matrix. For me to post multiply any matrix that shall have 3 number of rows, I will write some other matrix as 3 2 1. This is a 3 by 1 matrix. Since these two are equal, here number of columns is equal to number of rows there. So now I can multiply it. What would be the result? Resultant matrix would be of what size? 3 by 1. Okay, so let us perform the multiplication. 1 by 3, 1 into 3 into 0 into 2 plus 0 into 1. So 1 into 3 plus 0 into 2 plus 0 into 1. The next element will be 0 into 3 plus 2 into 2 plus 3 into 1. The next element will be 1 into 3 plus 5 into 2 plus 1 into 1. This is the resultant matrix of size 3 rows and only 1 column. The resultant I can just write it as 3 plus 0, it is 3. This is 4 plus 3, 7. This is 3 plus 10 plus 1, 14. This is my resultant matrix. Another example I will give you, because it throws some light on another aspect of the matrix. Say suppose I have a 3 by 3 matrix or 2 by 2 matrix 1 0 0 1. This is my 2 by 2 matrix, and I have another matrix x y variables, or I will take some numbers for that matter. Say suppose 2 3. What would be the result? Let us find 1 into 2. First of all, if it is possible to multiply them, let us check. This is 2 by 2. This is 2 by 1. Since these are equal, yes, matrix multiplication can be performed. Now, what is the resultant matrix? 1 into 2 plus 0 into 3. 0 into 2 plus 1 into 3. So what is the result? 2 plus 0, 2 only. Here 0 plus 3, 3 only. If you see this matrix properly, I have multiplied a matrix here. 2 3 is the column vector with a matrix here 1 0 0 1. When I multiply it, it actually did not change it. So this matrix, like in normal scalar multiplication, where any number you take x, for example 2 3, whatever number you take, if you multiply with 1, the value does not change, it remains same. Correct, right? In normal numbers. Okay, in numbers. Similarly, this matrix has that significance if you can properly observe it. You multiply this kind of a matrix with any matrix, it does not change the matrix, it gives you the same output. That matrix is called, that's why this matrix is called identity matrix, which after multiplication does not change the identity of the matrix being multiplied. That's why this is called identity matrix. So let us see one more example into matrix multiplication here. I have a matrix here 2 0 0 0 2 0 0 0 2. Okay, I have a vector here. I'll say 1 1 1. This is my vector. I am multiplying these two. Multiplication is feasible or not? This is 3 by 3 matrix and this is 3 by 1 matrix, a single column vector. So these two are same, columns in this equal to rows in this. So multiplication is possible. Now let us proceed ahead with the multiplication. So the resultant is 2 into 1 plus 0 into 1 plus 0 into 1. 2 into 1 plus 0 into 1 plus 0 into 1. And here 0 into 1 plus 2 into 1 plus 0 into 1. Similarly, 0 into 1 plus 0 into 1 plus 2 into 1. The resultant is 2 plus 0 plus 0, 2, 0 plus 2 plus 0, 2, 0 plus 0 plus 2, 2. If you see, the initial matrix is 1, 1, 1. And the resultant matrix post multiplication is 2, 2, 2. What has happened is it just got doubled. Correct, right? It just got doubled. If you see, here the number is 3. In all the diagonal element is equal to 2 here. Sorry, not 3. All the diagonal elements are equal to 2 here. When you multiply this with a matrix, it got doubled. If assume if all are 3, what would have happened? Assume if all are 3, I will keep it here 3. Okay, now what will happen? 3 into 1 plus 0, 0 into 1 plus 0 into 1, it will become 3. And here 0 into 1 plus 3 into 1, it will become again 3. 0 into 1 plus 0 into 1 plus 3 into 1, it will also become 3. See, whatever number is there here, it is getting scaled by that number. Earlier 2 was there, it became double. Now 3 was there, it became triple. Means the original matrix has been multiplied by that much number into 3. Earlier it was into 2. So these kind of a matrix usually scales the matrix to which it is being multiplied. Okay, here 1 1 1 was there, it is now became triple, means into 3 actually it became. So this kind of a matrix are called scalar matrices. Why they are called scalar matrices? Because by multiplying this matrix with any matrix, here I have multiplied with 1 1 1, I would rather replace it with some general matrix, say suppose x, y and z. Okay, x, y and z. What would be the resultant? 3 into x plus 0, 3 into x plus 0 into y plus 0 into z. Here it is 0 into x plus 3 into y plus 0 into z. This is 0 into x plus 0 into y plus 3 into z. So the resultant is what? If you see 3x plus 0 plus 0, this is 3x. 0 plus 3y plus 0, this is 3y. 0 plus 0 plus 3z. So the given matrix was simply multiplied by 3. So that's why these are called scalar matrices. What will be there in scalar matrices is, on the diagonal there will be an equal number, non-zero number, and everywhere else there will be zeros. If you multiply this matrix with any matrix, it will be scaled by that particular number what is present in the along the diagonal. That's why these are called scalar matrices. These are somewhat similar to identity matrix, where instead of any other number, here 1 will be there. The identity of the matrix will not change.